All right. Good morning, everybody, and good afternoon, good evening, also, since we are all across the world. So it's my great pleasure to have Professor Lima from University of Tokyo and to present his work. He is the latest inductee in the Autoware Centers of Excellence. Professor Ma's research is very exciting. It's on assured autonomy, so really bringing in testing, software engineering, verification, but to learning-based systems. He's a associate professor in the University of Tokyo, where he has also an honorary title of Excellent Young Researcher. And also at the same time, since being a professor in one university is not enough, he's previously and still currently professor and from the University of Alberta. So he spends his time, between the two places for now. And he's also a fellow of the Alberta Machine Intelligence Institute. And so Professor Ma, his work to the Autoware Centers of Excellence is very, very relevant because it's focused on, trustworthy software engineering, but with a human-centered focus. And it's essentially looking at, safety and security assurance for these cyber physical systems. Autonomous vehicles is one such example. And he's published in so many top tier, AI and software engineering venues like from ICML to NeurIPS to AAAI, IJCAI, and ICSI, of course, and has many awards and 6 of Distinguished Paper Awards. So today he's going to talk to us about a lot of his research, his past and current research, and I welcome you to join us. So Professor Ma, please go ahead. It's our pleasure to have you here.
Yeah. Thanks, Rahul, for the very comprehensive introduction. And hello everyone. So it's really great pleasure to be here and to present some of our past and ongoing work. I hope this is a great opportunity that we can, for example, establish some new directions for future collaborations under the framework of Autoware Foundation. So basically, I'm currently as Rahul mentioned, I have a shared appointment with University of Tokyo and the University of Alberta. So our research group actually has two big main goals. One is trying to think about how to design and develop the foundational methodology and engineering support to build the trustworthy intelligent software systems. So this can be is actually a very emerging, recently interdisciplinary field among software engineering, AI, security, and HCI, so on and so forth. So this is a bit more on the foundational part. And with this foundational methodology that we develop, we actually tried very hard in the past few years to adapt and apply these techniques to different application domains. Some are on the more cyber systems like video games, web, mobile software systems, blockchains, Web3, something like this. It's more like a completely software created environment and world. And another, actually, I think is highly relevant to Autoware Foundation is about the cyber physical systems, because there's an increasing trend of digitalization and more applying this AI to promote the performance of the like cyber physical systems across different application domains. Especially this is happening now in Japan. So I think this is a really exciting topic, and we have also spent a lot of effort on that. So currently, our labs just scattered around Canada and Japan. So because I recently, actually early this year, I joined University of Tokyo, so the team is still establishing mostly since early this year. And now we have roughly 15 members, some of our exchanged and visitors. But next year we will have roughly around 20 members. So we are moving very fast because the field is also moving very fast as well. So over the past few years, we have a lot of collaborations and grant funding agencies from different places. So as I mentioned, I really hope that with this new Center of Excellence, we can facilitate more exchange of collaborations around the world, especially on this trustworthy assurance topic for intelligent software and the systems. I think this will be a really exciting topic for the next few years, especially in the autonomous driving context. So basically, here are some of the high-level broad view that I have think about some of early stages around the center key topics. For example, on how to, to design and develop the comprehensive quality safety assessment criteria for intelligent vehicles under different lifecycle stages, and how to automatically provide the quality assurance like a methodology, toolchain support, so that we can, for example, detect these potential issues, security issues, safety issues, and understand and debug these potential issues, why that happens, and how can we enhance the safety in some human-involved ways. And with that, another big role is that we think we have a lot of data collected. I think this plays a really key role, the data-centric way of developing the intelligent solutions for many modules of the autonomous vehicles. So how can we better manage from the data-centric point of view to achieve or approach the safety assurance? I think will be a really interesting one. So this is just a very high-level, rough idea on some of the possible directions I'm thinking about. But definitely, it's really great if there are some feedbacks from you, and we can discuss, for example, which could be more feasible and promising direction to go and move forward. So basically, if you use one big picture to summarize some of our work, so at the very bottom will be the foundation, what I have just mentioned about the trustworthy intelligent software engineering. So basically, it centers around the pipeline or development lifecycle of the data-driven AI systems from the data model building, system building, testing, verification, deployment, maintenance. How can we provide the systematic toolchain and methodology support around this lifecycle? So this is more of general purpose AI models or systems. But when we go to a particular domain like robotics, self-driving, so there could be a lot of domain-specific context and the knowledge and know-how. So how can we better design and adapt these foundational techniques inside these domains is actually a really, I think, personally interesting topic we have tried. So I would like to first give a big background on why we really care about these data-centric or data-driven AI. So especially in the past few years, we see a lot of applications of data-driven AI around many application domains. So, and with the very early, this is 2018, this is a survey, industrial survey by McKinsey around actually, I think it's 19 sectors of different industrial domains. We see there's a really big potential of the only deep learning at that time surveyed by this research. So how that will be valuable to these different industrial sectors. So we see a really big movement since 5 years ago, actually. This year is a very special year because we see another high rise of the AI, generative AI in particular. So we see a really exciting applications. So some of the examples, like especially these are diffusion models from last year. So for example, I gave a really simple example to generate a cartoon style image of Tokyo with Sakura. So this is by DAO-E. This is last year's version. So it gave a really interesting one. So this sketched version. And on the right-hand side, there will be a stability AI by using different models to assist how to promote these artificial or art creation or content generation. And but definitely I think everyone now knows the OpenAI's ChatGPT. So this is a really exciting move.
Mhm.
So yeah, according to the McKinsey, they do another actually survey this year. So we see the applications of the AI and AIGC in the next few years will be another big boom. So we think there's a lot of opportunities ahead. But on the other side, there's a always consistent problem remains is about the safety, security, and the quality of these AIs software system when we apply them to real world systems. So these sidelines are basically everywhere. And I think in the last few years, companies are trying to bring these applications very quickly to the market, but I think less concern or not very regulated way. So I think that since last year, there are more and more some of the regulations and laws come into the real world stage. So I think in the next few years, this might be a really important one, mostly on the trustworthiness when we use the AI in the real world systems. So here is a very simple example, but interesting one. A few years ago, so the Honda, the car, the perception part of the Honda actually uses the deep learning classifiers to recognize these traffic signs. But there is actually a really famous Japanese ramen or noodle shop. It's called Tenkaippin. So you see here, the logo is very, very similar to the you cannot enter. It's a one-way traffic. So then what this signals to the driver is that whenever you see this ramen shop, then there is a perception that you should not enter in some sense. Yeah, so yeah, there's a really big the issues posted on the news at that early stage. But actually this is just a very representative one. I think many of the applications of AI in the real world, especially regarding the safety, security, quality, or other like copyright fairness, it becomes a really big concern these days. And a few years ago in Japan, the JST Research Center actually created a domestic survey on how the Japanese market, when they use AI, what will be the potential value and how much reliability the AI would be if they want to use them in that domain. From this simple statistical numbers, we see, especially in a manufacturer-oriented or focused industrial landscape, if the Japanese companies want to use AI, many of them require that to be like a high or at least a medium dependability in some sense. So that's actually from 5 years ago, there are some national strategy and activities to create and develop some program to do research along this direction. So then you might ask why what makes a big difference from the like machine learning, data learning based software system to traditional software systems or other like control systems. So one big difference is that we have very fundamental different development paradigm. So in the old days, we mostly rely on the professional software engineers, developers, domain expert to write the source code models or other argument to create these system artifacts. And then basically we have a really nice understanding on that. But nowadays, many of the data-driven AI software models or components, they are actually learned from the data. So the developers or the engineers role just changed from like have a really deep knowledge on that particular domain. Instead, they try to collect relevant data, maybe label the data, and then learn the decision logic automatically. So it really lacks a good understanding from the human perspective what the decision is about and why, for example, an AI model make that decision. So this is actually, I think, the very fundamental change that makes things really hard. And that's also the reason why, from the safety assurance, quality assurance, trustworthiness assurance point of view, many of the existing technique we have for traditional software and systems, actually we have for many years. Like it's not new. Like we have like credit card automatic judgment or decision system. We have the algorithm in the old days, but nowadays the change is that since many of the decision logic is really hard reasoning, development paradigm changes. It's more data centric. So old days technique mostly cannot be directly applied in this new data-driven development context. So that makes fundamental changes. How can we rethink about this issue in terms of safety and quality for the new era? So another thing is that the real world AI systems are often very complex in some sense. So here is a quick example. We made a survey on Apollo autonomous driving systems actually 3 years ago. So we only look at mostly look at the perception part, that the different modules and models process the different sensor signals, image, lidar, and radar. So only this perception part, the Apollo contains more than actually 20 machine learning models for different kind of purpose. And eventually these signals are sensor propagated and fusioned for later planning and controls. So here I just use this example to show that for each individual AI model, we don't have really nice understanding and methodology to guardrail its risk and safety properties. But when we combine them together, it becomes an even more explosive, challenging problem. So, and in many real world AI systems or AI software are indeed very complex. Here's another example of AlphaStar that developed by DeepMind to play the StarCraft. So it's a 5vs5 games. So here is a simple pipeline to show how they actually obtained, represent the world, represent the players, represent the like metrics, goals, reward, and how to put this pipeline together to train this intelligent agent so that they can play the games like a human professional player. So yeah, here again is really complicated and a lot of engineering effort goes inside this. Yeah, here's another simple example of an intelligent audio system. It also contains a lot of stages, and each of them can be a really huge, module inside itself. So in general purpose, trustworthy assurance of AI, there is, I think several years ago, started to push this ISO IEC GTC IC42 about the trustworthy AI. So there's different kind of working groups. I think it's also highly relevant to the context of autonomous driving, although autonomous driving had more specific safety assurance like ISO 26262 or SOTIF liked standard. Yeah, here's a few that relevant guidelines are under development in Japan, I think in EU and IEEE as well. Okay, so here are some of the background I have just introduced. And for our research, we started a bit early, I think so, roughly from early 2015. So roughly it's about 7 or 8 years. And at that time, the model are still not very complex. But as the time changes, the model becomes more and more complex in some senses. So, but the methodology, I think the experience accumulated in the past few years, I think is really valuable to help us to understand about the trustworthy and quality assurance for the AI, both at the different levels and different lifecycle stages, and also different application domains. So here, due to the time issue, I will just briefly introduce some of the ideas of high-level ideas of quality assurance for like a unit level quality assurance for AI models, big lightweight touch on system levels, and more. I think I would like to focus on the our work on the cyber physical systems. Yeah, so here is just give an overall high-level discussion. So the purpose is not to discuss itself, but more to facilitate how we might, for example, work together across the different working groups and the centers in the next stages. So for the unit level, so we mostly focus on like the model, one model at a time across its life cycle. But since the data-centric AI model development, it also involves data and code. So basically, we need to consider all of these three types of artifact at the same time at different stages, like a data preparation, model building, training, evaluation, testing, verification, deployment, and continuous CSD stages. So, and around this lifecycle, we make some work, and some of these tools, I will briefly introduce the idea later. And this is at the model level, but at the system level, we need to consider both of the AI models or AI modules, as well as traditional software component. Because as I mentioned, usually the AI system is composed of different components that some of are still by traditional software, some are by the AI models. So that at the system level, we still have another life cycle we need to consider because different pieces might evolve from time to time. And some may be upgraded or some may be replaced, so on and so forth. And another very important thing is about how can we make the application of the system responsible so that when some issue or some safety concerns or safety accident occurs, we need to know or help us to know where the issue happens. So here, we really want to have some kind of a more human-centered, interactive way to help us along these different stages, like whether it's a problem with the data, model, software, or system at different kind of stages. Yeah. And last week, 2 weeks ago, actually, we have a Xiaonan meeting at focus on the cyber physical system and DevOps. So how to consider bringing or bridging these development ops with the cyber physical system to enhance the safety of that system. But as more and more AI models get involved, maybe have different kind of purposes. So how can we actually still can guarantee this? The safety is one of the biggest problems. Yeah. So yeah, let me quick get started on the foundational part. As I mentioned, first at the model level, we need to consider both transition software and AI software. And for transition software, actually, we have a lot of research result, outcome, industrial experience, and best practices. And some of the standard are already there, so more than 30 years. But for the AI models, we don't have that. So that's actually we try to think about it at the early stage. So because this is actually a very, very big field, so some of the content we focus may be somehow narrow. So here we mostly consider from the standard tools to detect the issue, analyze the issue, understand the issue, debug and find the root cause, and then how to fix it in some sense. It's more like a software point of view. So we first at the early stage to consider the test criteria and quality indicators for the AI models to better understand how can we get some kind of estimation using metrics to understand, for example, how sufficient we test the AI models and how good the AI model quality is about. And with this criteria, we can easily translate and use it as a goal or target to guide the defect detection tools to help us to more efficiently detect the safety issues or quality issues of the AI models. And then with that kind of detection, we want to, for example, also like a program analysis or software analysis in traditional software, whether we can do some kind of analysis for the AI models to understand its behavior and understand what kind of major behavior patterns that could be from this point of view. And based on that, to better capture or categorize the capability boundary and to understand its risk when it's used in practice. And with this understanding, we hope also to make more of these techniques more interactive so that a human developer can get more tangible to interact with these tools to understand what the model's behavior is and why that decision is made in some sense. And after, for example, we understand the reasons of the model issues or quality issues, whether we can propose some kind of enhancement or repairing technique for different kind of contexts. So this is a rough idea and the relation. They are mostly that think about these ideas as a pipeline, how we can equip these AI development model lifecycle with these tools to enhance the trustworthiness in the whole pipeline. Yeah, and very early work is about this testing criteria design. So the idea is based on this assumption that since the data-centric software, we really need to consider the role of data with the model. So only we see the model, we really don't know what behavior it is about. So how can we design a test criteria or quality assessment indicator to enable the quality approximation by observing internal, neural behaviors or feature behaviors, and so that can provide some kind of guidance or indication to help us to understand, for example, when we test, for example, when we do analysis, whether it's sufficient or not. Yeah, so the big difference from traditional software is that since it's data driven, so one big fundamental assumption around the statistical machine learning is that about the data distribution. So the assumption is that when we solve a particular problem, the problem domain or the data, it follows some particular distribution. We say it's a training data distribution. So the training data is usually sampled from that that kind of a domain. And then we do some model design, learning algorithm design, and then we train, develop the model. And the fundamental assumption that machine learning theory can guarantee or somehow guarantee, approximately guarantee, is that when the future data we have never seen have a similar distribution of the training data, so they share similar distribution, then we can have the learning can give some kind of accuracy guarantee, like a 95%, 97% accuracy. So in that sense, if, for example, a model is trained to classify whether it's a cat and dog, eventually it is used to on other animal like a fish. So that's actually not relevant in some sense. So the data distribution plays a really important role to identify the behavior relevance of the models. So that's actually our early idea, is that the deep learning model or AI model is not just a mathematical formula or function out there. So its behavior is somehow defined by the training data in that particular domain. What we can do now is that we can sample or use the training data distribution. Then we can do some kind of statistical profiling analysis to understand the distribution or behavior distributions of each neurons or each feature vectors. Based on that neuron behavior and feature vector, we can define some kind of like a functionality measurement, like which will be the major functional region, corner case region, and so on and so forth. So it's more like give some kind of a quantitative measurement. So the idea then is quickly explored in different kind of ways, like when we consider one neuron, whether we can consider the neuron interactions, then it evolves into like a structural behaviors that can consider neurons in the same layer, nearby layer, or using all the layers neurons. But the problem is, how can we extract a really nice representation that ties the behavior of the model and our understanding in some sense through this internal feature vectors. So there are, this is still a research direction. It's really interesting one. Okay, so then, as I mentioned, with a lot of criteria we designed either by us or by others, researchers, then one interesting usage of this criteria is that it can give us like a goal, whether we want to provide better quality, then we can use that as a goal to drive the testing tools to detect and generate scenarios that can trigger that errors at an early stage. So this is one of the early work we have done on testing AI models. It's called Deep Hunter. So this is follows a very standard fuzzing framework and pipeline. So the key thing is that when we generate the new test cases or new scenarios, we usually follow some kind of like OOD And based on the OOD, we can design some kind of mutation or transformation operators. Like in the context of camera cases, there could be some kind of noises in different ways from the camera that can capture, and we can use this to generate or new test cases from the seeding images, so that can explore different kind of potential safety issues of the classifier. But how we use and how define it really depends on how the scenario is defined and what could be a really valuable thing we try when we generate test cases. And the key thing is that we can use this. The problem is there are so many mutator combinations, but how will be the effective way to do it? That is, we can use this kind of criteria to guide. We try to generate these different kind of scenarios, layer by layer and augmentedly in an augmented way. Yeah. So this is just a very early idea, and there are also a lot of recent work in these directions. Yeah. And after that, we just go into a more wild mode to do like a model-based quantitative remodel or re-engineering of these like AI systems or AI models, AI models. And with that kind of modeling, we can have a better understanding on this behavior. So here I'll give you more introduction of this on the recent large language models we have done. But here the basically build an analysis framework to understand the statistical behavior patterns of the AI models. And also we find that like auto distribution and uncertainty could be two really important ways when we try to understand the capability boundaries and the potential risk when we use the AI models in practice. So this becomes really interesting, especially when we look at how the AI model fit into the bigger system and how that behavior can propagate into the system behavior in some sense. Yeah, and some of these have also been applied in the industrial context to understand and counteract the potential risk when the AI models is used for prediction of the environment in some kind of manufacturing processes. Yeah. And with that kind of tools developed, we find that it's not very easy to use and not user-friendly. In particular, we found that developers still find it really hard to understand the behaviors of the models. Just only look at the numbers doesn't bring much more information to help them to debug the model behaviors. Then actually, this is this year's paper. So it's about DeepSeer to provide a more interactive explanation, the debugging interface for the AI models. So for traditional software, like we can just debug the code by reading it line by line. But for the AI models, deep neural network, mostly they are internally the feature vectors, all numbers. Like these recent foundational models usually have like billions numbers of parameters inside. So this is not really in the scope of human capability to understand this behavior, even debug it. So how can we do this is that we can actually make some kind of an abstract model representation or approximation from the original AI models, and then we make them visualizable to tie each kind of a model in the state with a concrete semantics. The semantics can be really diverse based on the different contexts. So for example, some of the like natural language processing context, some of the state like 5 or 32 triggered, then some kind of weird behavior might happen for that model. Then we can actually try to, so for example, to get avoids those kind of input that trigger these kind of state. We can say, okay, when the input triggers some of the danger or risky state, it goes into a really unsafe or uncertain decision. So then we might not trust it in some sense. So then here we provide an interactive user interface for the developer so that they can play with these states and how they combine with different training data, test data, and also the runtime data, and how they are binding together to better understand the whole process, to know what's the vulnerability and the weakness of the current version of the model, so that it can have better understanding of how to enhance the model in the next iteration.
So in this case, these states are some latent states, or?
This is actually another, for example, given some kind of state in the cyber physical system, we can rebuild like a Markov decision process model to approximate its original behavior. So which input segment will trigger which state, and then what will the output will be.
I see.
Yeah, and then because the training data is there, distribution is there, and then we can actually using all the training data ideally to extract or reverse engineer the internal behaviors of the AI models, and then the Markov decision process states will have some kind of statistical information. For example, like if some kind of input trigger 5, then among like 10% or 50% of all your training data actually statistically will be in a failure result. So then some of the states will be a very dangerous cases, but it really depends on how we define the semantics. We can later bind these domain-specific semantics into different states so that we can have some kind of analysis handler to do this thing. But how we do this statistical models extraction, we can use different ways, like Markov decision process or hidden Markov chain or other simple like discrete Markov chain. So different ways we can do it. Yeah. And with that kind of model, we can have better understanding on its behaviors. And with the interface, then the developer can play with it to see why the input triggers some kind of state and why that failure happens. So they can be combined with the training data behaviors in the past.
Thank you.
But the developers aren't thinking this way, though, right? The only problem is that they're thinking in their application context, right?
Yeah. So then, similarly, we also do a debugging on the data because the data is also very complex cases. Right. So how can we better understand the data behavior, their relations, like even the label errors, because the number of the data is really very huge. How can we better understand the data behaviors and its relation to the models? This is another work focused on the data part. Yeah, but currently, actually, we are trying to think about how to design the interface for more diverse stages of the quality assurance tools so that we can make all these processes more tangible for the developers, so they can, so it's easier to use, easier to see and observe,
well, just,
rather than
let me just, so I follow exactly what you're saying, and by the way, I do very almost similar work. Your slides, I could match my slides to your slides, and all that. But let me talk about because I'm going to have to leave soon. So I just want to talk about two ideas that at least we're pursuing, and maybe 3 ideas we're pursuing that maybe there's collaboration. And one is, one of the places AI is the most useful is when you don't understand the problem domain, unfortunately. So, hey, so this is like somewhat a conundrum for a validation person, where say, okay, well, I don't really understand the problem space, but I've built something. I don't actually know when and why it works, or in fact, if it works. Other than that, it works great. So so that being the constraints, one of the things that I've focused a lot on is what I call specification-less systems, where you imply, you can specify things 2 ways. You can have models, very hard to do, or you can define the converse, which is we would call them assertions. You make assertions about the design or assertions about failure modes, and therefore the antecedent of that is the definition of the system, right? So everything outside of the So a lot of the work, especially in cyber physical systems, but believe it or not, I think it's a much easier problem than like NLP is. We operate, for example, in Newtonian physics, right? So we can take advantage of that. We operate in a domain where there's interactions and there's real latencies involved and so on, and control systems. So these, from a validation point of view, turn out to be useful properties that can be used when you're looking at these kinds of models. So we could talk about this offline, but that's kind of how do you automatically build specifications in the language of the people designing these systems, right? Not in underlying pieces. That's one thrust. And then the second thrust is, for all this validation, we want some level of compositional properties. That is, we want the result of the perception stage to be verified separately from the location stage, and we want the composition of the two to work in such a way we can reason about them. We do this all the time, by the way. My background is in semiconductors, so we do this all the time in semiconductor verification. We independently verify disparate subsystems, and then we compose them to build an overall argument for the whole chip, right? So what are those similar things? And they tend to be system level behaviors versus underlying model behaviors, right? So in AV systems and airborne systems where we do a lot of work in this area, that's the second thing. And the third thing is, one of the things that happens, especially with AV, is there are implicit communication mechanisms on the human side. I noticed you mentioned human-machine interaction that are actually not specified, but it's actually worthwhile to specify them and have some methodology for specifying them. So I mean, I just leave it there. Those are the three areas. And my interest in Autoware is essentially as a test bed for building these ideas, and then my sense is that as you build these ideas out, as an example, when we do your component level checking, which is a very important thought, right? How do you take component level data processing and ODDs, and how do you intersect them? To do that in a non-domain context is difficult to impossible, right? But if you impose a domain specification, for the lack of a better word, on top of that, then at least you have a way of reasoning about the data, right? Yeah. Anyway, we could talk offline. I think it probably will be worth offline to talk, you and I, to get together so we can show you what we're doing. And
Okay. Yeah, perfect. Yeah, thank you. Yeah. It's really nice. Yeah, feedback. Yeah, and let me continue. So with that kind of analysis, we also try to think about whether we can enhance the behaviors or repair some of the incorrect behavior in some sense. But the very challenging thing is that for deep neural network behavior, that could be a lot of potential sources of issues that can cause these incorrect decisions. Like it can be the model issue. So the learning is not actually well trained, for example. And there may be some kind of issues in the data. The data is not in a good distribution sampling, or the data label is incorrect in some sense. So and data may be insufficient in some of the categories and more imbalanced distributions. And further, in the operational environment, when the system is deployed or model is deployed, there could be kind of distribution and concept drift or shift, in the sense that our future expectation is not consistent with what we learned the model is about, or it's a kind of a shift about this kind of expectation. So for different kind of reasons, there could be different kind of ways we need to fix it. It's not a universal enhancement or repair technique out there. Yeah, in some sense. So in that, actually, 3 years ago, in Japan, we have a GST, we call MILAI, or Engineerable AI project. So that's trying to think about whether we can provide some kind of engineering support to enhance the safety and the quality of the AI models for industry usage. And in our context, on our team, we mostly focus on one very concrete direction, is that when the AI software or system is used in practice, there could be some kind of noises or corruptions happens for operational environment. That typically happens for camera, for example, the kind of different kind of noises that can occur for the lidar and also for the radar. So we think about whether we can do something if we know the context, when the AI system is deployed in the real world. So we try to focus about this on the two big directions. One is from the data augmentation perspective. In a sense, we try to remodeling the usage of the data distribution in the operational environment. So that might be slightly changed from what we have learned in the training environment or clean environment, so that with the better understanding or modeling these or learning these new distribution in the new context or operational environment, we try to see whether we can just to do more fine-tune or data augmentation based fine-tune to enhance the behaviors in some sense. And from another perspective is that we try to think about whether we can search or find a better alternative, the neural network architectures, so that it can be in nature be some kind of more resilient against different kind of potential noises that occurs in the operational environment. Yeah. So yeah, one of this work is also reported by the Nikkei Shimbun News early this year. So yeah, basically that's a very high level introduction on the unit level quantitative assurance we can do. And at the system level, it becomes actually more complicated because we need to consider different components as just Rahul mentioned. Yes. So so basically in the system level, things become much more complicated, and a lot of issues can occur in this process. So like from the source code, like in the models, and also from the different stages of this system, in a sense. And again, it poses a question: is what would be a good quantity indicator, measurement, metrics, or criteria for us to better understand how good the quality or safety is about, and whether we can have some kind of quantitative measurement to help us understand this risk in some sense. Yeah, and actually, I cited a paper from Joshua that he published actually in ICSI 2020. So this paper, I think, is really nice summary on the potential bug categories and what potential issues might occur in the autonomous driving context. Both, I think there's Autoware is also there, and also Apollo. So, and for us, I think it's really nice to understand with these many potential issues, how can we fix it or understand this behavior, or understand whether we can do something with it. So then following our previous work on the Apollo pipeline analysis, then we go one step further to see whether we can do something on getting understanding on the potential risk of each individual model or component, either from AI or alternative software, can propagate to the system decisions in some sense. So that can be really helpful for us to understand when the system error or failure occur, which of the modules could be more suspicious to cause the issue, and which of the component could be the bottleneck of the system. If we want to improve or iterate for the next version of the system, which one we should prioritize to look at. So with this goal in mind, we do a joint work with actually Fujitsu in their inside AI system pipeline. So we developed a tool called Cabits. So the basic idea is considering the like from the auto distribution perspective or uncertainty perspective, from both each individual modules and how these behaviors or uncertainties can propagate from one module to the final system decisions, and whether we can establish some kind of connections, like correlations between them. And eventually we find this could be a really interesting idea to further look at. And here, this is the one we really want to see whether this idea can be somehow helpful for the Autoware to better understand the system behaviors. And I think we have a lot of things we can do here. And we can keep the discussion about this later. And early last year, we completed another work to analyze the existing fusion modules in the autonomous driving context. And we found that because of the fusion module really is used to process the sensor or intermediate sensor results or features from different kind of sources of sensors. So then actually from one or several sensor failures or issues or potential kind of corruption data, then it might cause some kind of potential issues. We at the beginning, we think that for many of the mature system, it should be some kind of a resilient against these kind of sensor failures and issues. But in reality, we found that it's not exactly like what we thought. And the existing fusion components or algorithm are still not be able to really robust against different kind of corruption patterns on the different kind of sensor types. So that makes us think about whether and how we can get rid of this, or at least detect these issues at an early stage. So that leads us to our very recent work on whether we can do some kind of reconstruction of the, or we say that we have the one type of sensor data, another type of sensor data, whether we can try to reconstruct another multimodality data so that that can be used to simulate what can happen in real world. Because in the real world, we only have limited kind of data. Some of maybe one channel, one model, the other maybe another model. But how can we combine them together to reconstruct some kind of a multimodality ways of the data so that can be used to simulate the real world sensor cases to find the potential issues at an early stage. Yeah, I talked with Xinpei about this. I think he have a lot of I think Autoware may have some kind of a data that might be available to consider whether we can do some kind of like a word modeling construction so that can help us to better reconstruct the testing scenarios or driving scenarios to understand the potential risk of the autonomous driving different kind of stages of system decisions. Yeah. So basically, here is a very high-level rough overview of what we have done on the foundational part of the intelligent software system to make it more safe and trustworthy. And another direction we are trying to do is that push this to cyber physical system domain. But I think I don't have much time on that. But let me quickly go through what we are doing on this. So the basic idea of CPS, I think many of you are maybe very, very familiar about this, is that we have a loop of control and manipulation target, usually like a plant. So we have used the sensors to collect the information of the plant and using a controller to make decisions and on what we should operate the plant by through the actuators. So with this simple explanation of the cyber physical system, the AI system, there could be a lot of potential roles occur in the recent years. I think there's a lot of community are trying to do this as well. Yeah, so like a control, doing form as a controller, predictor, monitoring, scheduling, safety security analysis, and prediction. So there could be a lot of roles of AI for the CPS context. And again, so there could be a lot of existing solutions because CPS is not new, and a lot of tools available like falsification model checking, reachability analysis. These are very fundamental ones to provide the safety guarantees of the CPS when they use in practice. And then the problem is when the AI component get involved inside in some of the roles inside these CPS, what we could do to consider the safety guarantees. So then we found that actually in the CPI context, there's a lot of things we need to consider, and it's not very systematically studied when the AI is involved. So then we actually, at the early stage, we create AI-enabled cyber physical system benchmarking from those that are open source and publicly available. So many of the cyber physical systems are mostly developed by some kind of traditional manufacturer or industrial companies. Many of them are top secret. So from the research point of view, it's really hard to get the information on that. So we hope that this work at the beginning to create some kind of a publicly available cyber physical system subject so that we can do more analysis on that. And then with this target AI-enabled cyber physical system benchmark or subject we created, we do more systematic analysis from the defect detection point of view to create automatically defect detection tools called falsification. And then after finding the issues, we also hope that whether we can do some safety enhancement from like understanding, again, try to understand the behaviors of the AI models inside the cyber-physical system, and then try to understand this context to leverage that understanding to enhance the behaviors in terms of safety. Yeah, and here's a few things we are doing. And let me skip this because time. And another thing, actually, we 2 years ago we started to do a joint work with NVIDIA to create like a universal AI-enabled cyber-physical system under the NVIDIA Omniverse environment. So the biggest advantage of the environment is that they provide some kind of simulation environment that can accelerate the computation learning by the NVIDIA GPU. So here we started because of this opportunity, and I think we can actually mirror many of these ideas we have with this collaboration into the Autoware part, both from the Autoware itself and also the simulation. How can we, from the simulation point of view, to better provide the safety analysis and guarantee in some sense, and how that can be transferred further from the software in the loop to the hardware physical cars. Yeah. Yeah, and more of the recent work we are doing is more centered around the, just as Rahul mentioned. So if we have a better understanding on the domain, and if we have some rough kind of properties of the regarding safety, whether we can automatically design some reward function by language models to to automatically learn some kind of controllers that can be somehow safe or complement to the existing controllers, how to do that, and how to perform like a safety guarantees on both the learning process and also the behaviors after integrating the models into the cyber-physical systems. And we are also doing one thing in parallel is to whether we can do some kind of a translation of the natural language-based description by some domain knowledge domain expert to describe the properties in natural language. We want to think about whether we can translate this description, its kind of informal specification, into more formal specification based representation, so that these properties can be automatically checked regarding the safety point of view. Yeah, but in the long term, we really hope we can provide more systematic way regarding the safety assurance, both during the construction stage and also provide quality assurance at different kind of life cycle stages to achieve the better safe results of the AI applications in the real world. Yeah, and another big scope regarding cyber systems, let me just skip it. Yeah, and one last thing I want to maybe like to say is about the large language models. I think this might be somehow interesting. I'm not sure what the stages of Autoware, whether large language models could be a potential applications in the Autoware in the next few years. But what we are doing is that we try to think about whether we can create a general purpose or we say universal analysis framework for large language models to better understand its potential risk when its usage, to better understand whether it's robust or not, and to reason about the behaviors when the large language model gives one particular outcome or prediction. So we can do some kind of safety or security guardrail. Yeah, so yeah, and we do it in both black box ways and white box ways. So the black box ways, we only can access a model through the API and we get a result. We don't have any other information. So then what we can do then we can basically take advantage of only the available information with the input and output, try to reconstruct the behaviors models from the uncertainty point of view. And with more, like we have the access to the model architecture like Llama, then we can do much more to create more systematic reconstruction of the human understandable statistical models to capture the internal behaviors and behavior patterns. Based on that, we can design a lot of analysis techniques. So many of our lab members are currently working on this at this moment, and we hope that there will be some kind of interesting result coming out soon. Yeah. Thank you very much. So I think it's roughly 1 hour, and yeah, I'm really happy to answer questions.
This was amazing. I think you have material for at least 6 talks over here, half a dozen different and each one is a very deep topic, but I think you gave us a good overview, and it would be very, very useful to have follow-up discussions on many of these. I'd just like to open it up for any questions people have.
Yeah, I think we can also maybe have some follow-up questions later.
Yes.
Yeah, because we can communicate. Yeah.